welcome you all to the SET Digital Software Engineering Transforming Our Digital Futures Research Seminar Series. For those of you who don't know me, my name is Noor Ali. I'm a senior lecturer at Brunel University and the organizer of SET Digital. I'm so excited to see audience actually from outside Brunel University. I would like to welcome you all for attending SET Digital. So just to give you a brief introduction about SET Digital, it's an initiative funded by Brunel University, and its objective is to disseminate software engineering solutions which are innovative breakthroughs to lead goals and challenges for the digital transformation, and highlight current challenges faced by industry in the digital transformation. We also would like this event to put up an opportunity for networking between academics and industry. So this is the first talk in the series, and I wanted to go through a couple of housekeeping notes. I know you are all muted, but if any one of you needs to give a question while the seminar is going on, please raise your hands and I can unmute you. Also, if just to let you know, if you could turn off your cameras during the talk. And finally, please as well raise your questions on the chat, and just to remind you, the seminar is being recorded. So I'm so excited to have our guest speaker, Dr. Manuel Ángel Serrano. He's an associate professor at University of Castilla-La Mancha, a member of the quantum scientific research team at Alarcos Research Group, and he has been working recently in the area of quantum software engineering. His talk, Quantum Computing Concepts Towards a New Programming Paradigm, will be giving us a tour on quantum concepts that are fundamental to start in this quite innovative world of quantum software engineering and programming. So I invite you all to welcome Dr. Manuel Serrano. Thank you.
Okay. Thank you, Noor, for your great words for the presentation, and welcome everyone to this this speech about quantum computing. In fact, quantum software engineering is not enough mature to be a discipline. We are working on that, but well, I think that we are going to try to understand the principle, the initial concept about quantum computing. I'm going to share my screen. Here is it. I guess that every one of you are seeing my presentation, and I want you to invite you to send me an email after the speech, or whatever you need, you have questions or something like that. Okay, so let's start. I have no problem if you have any question. You can write the question in the chat, and we try to make this as most interactive as we can. So. What is this? This is me. I am not going to tell you more about me because Noor have presented me before. But how is this about quantum computing? Well, probably you have heard about quantum computing or quantum mechanics in the movies, on TV or something like that, and probably you have heard about the not intuitive part of the quantum mechanics. So trying to get into this kind of computing field is something like this cartoon, because probably things are going well or have not even started. So we don't know, because is this technology mature? Probably not, but it's going to be. Probably yes. Can we observe this this kind of evolution of the quantum computing? It's a tricky question, because everything in quantum computing is under heavy research. Well, this cartoon is about two of the characteristics of quantum mechanics. Is because we can be on superposition state, and even it's difficult to watch to see the state of a quantum system. We can talk about it later, but let's start about why quantum computing. We have to go back to the ancient Greece. In the year 400 before Christ, Democritus thought that the matter was made of something like small balls that they call atomos. Atomos, that it means not divisible. Okay, but it was true? It wasn't, because something inside this kind of atomos was. So people had to understand what was inside this. But the best thing about this atom concept is that those atoms, and even everything we see around us, can be seen or can follow the Newtonian physics. So we can understand everything we see, because if the apple is falling down the tree, we can understand that it's going to be on the ground. But in quantum mechanics, it couldn't be that way. Let's back from Isaac Newton back to the ancient Greece, and you can see this painting that is in the Vatican City. This is the School of Athens. It was painted by Raphael, and in this painting we have the great sage of the ancient world: Pythagoras, Aristotle, Thales, and Hypatia. There is a lot of people here that was great minds at that time. But all of these people think about the matter, about the nature, about the things around us in a macroscopic way of seeing things. But like if Raphael was some kind of visionary, this kind of a School of Athens was replicated at the beginning of last century in the Solvay conference in 1927. In this picture, you can see, probably, you can recognize Albert Einstein. But this is a very interesting picture, because here was where the most the great minds at the moment. It was Marie Curie, it was Pauli, Schrödinger, de Broglie, it was also Lorentz, Max Planck, Pauli, Heisenberg. This was a very exciting moment in the history of the physics, because in this conference in 1927, all of the quantum mechanics ground founding were established. And after that, we can be here understanding what is inside those atoms, and and how we can use this in order to make some quantum computings. But the bad thing about that is that we are in something similar to the middle part of the last century. This is a picture of the ENIAC computer in 1946. As you can see, there is a lot of wires connecting parts of the computers. This is similar to the situation we are in quantum computing, because we are wiring this kind of quantum computers. But we have an advantage. At that time, the ENIAC can make 5,000 operations by second. This was good for the moment, but now we have a lot of more power in our computers and even in our mobile phones that we have in the pocket. And now this is the more powerful computer from IBM from this year that can perform 200 petaflops. This is something like 200 per 10 to the 15 operation by second. This is a lot. But this kind of classical computers can perform some kind of algorithms, optimization algorithms or simulation algorithms that cannot be approached by classical computing. So we need another kind of approach for these kind of problems. Because with classical computing we have some kind of tractable problems, but for example, simulating chemical molecules or making some kind of optimization problems could be impossible to get the solution in our lifetime. So this is the promise of quantum computing. Can solve this kind of problems in another scale of time. This is good and this is bad. We are going to talk about that because there is a lot of problem with that. But let's go on. What was the born of the idea of quantum computers? The quantum computer was invented or idea by this guy, Richard Feynman. He was Nobel Prize in Physics in 1965, and he talked that in order to simulate some kind of quantum systems, real quantum systems, we cannot do that with classical computers. So he asked the question about why not using the quantum nature of the matter in order to simulate quantum mechanics systems. And this was the idea. But we had to wait for about 50 years in order to get to this moment that probably is one of the most exciting moments in the computing field. But we have another problem, and is this, that Richard Feynman said that if you think you understand quantum mechanics, then you don't understand quantum mechanics. And this is true. When you try to understand the quantum mechanics, you realize that you don't understand that. And how can we program a computer with something that we don't understand? This is a real problem. But there is a lot of research, and we are trying to understand quantum computing algorithms, not trying to understand quantum mechanics. And there is a lot of interesting initiative in this kind of computing, so we can get into that. Well, this is a quantum computer, but this quantum computer is not all you see in the picture. The quantum computer, I'm trying to here, okay, here, quantum, it's not working, the quantum computer is this part below, in the lower part of this structure. Only this is the quantum computer. All of these in top of it are wires, are a socket, something like that. But the quantum computer is very, very small part in the bottom of this thing. One of the best thing about quantum computer is that it can be small. The bad part about this is that they can be refrigerated in order to work, and they had to be near absolute zero, near minus 273 Celsius degrees or 0 Kelvin degrees. Okay, we have a quantum computer. Let's go on. As you can see, IBM, Oxford, Berkeley, the Massachusetts Institute, the Stanford have the first quantum computer around the end of the last century, but they only have 2 bits. We only have 2 bits. With that, we can prove that the quantum computer was something that could be done, but we have not a lot of quantum computing power in order to solve problems. But things have escalated too quickly. And as you can see, here around recent years, we have more than 100 bits. And this is a lot, because 1 qubit is a lot more powerful than a classical bit. And we are now in a situation in which quantum computers are real and can solve a lot of real problems. But this is also a bad thing. This is what is called quantum supremacy. Quantum supremacy moment can solve those kind of problems that shouldn't be solved. What is this kind of problem? This kind of problem is this: the integral factorization. Why? Because this algorithm is the base in which the public key cryptography is based. Until now, nobody can break this kind of cryptography with a 2048 bit key, because we need more than 1,000 million years. But with an algorithm invented in 1984 and with the actual quantum computers, we can break the RSA public key cryptography. And this is a real problem, because credit card payments, bank connection through internet, HTTPS protocol, and so on, are based on this kind of cryptography. So with around 50 or 60 qubits, we can break this. And these are bad news. So we need to invest in post-quantum cryptography, another kind of cryptography that cannot be broken by this kind of quantum computing. But the good news are that there is a lot of applications for these new kind of algorithms. This is what I call a quantum future. And you can see that material science, chemistry, optimization, pharmaceutical, financial, including services are going to be changed by this kind of quantum computing. But for the people that are working on this is probably our best birth control system, because you cannot get a Tinder match if you put on your profile that I work on Hamiltonian complexity. So this is one of the things we have to liquidate. But not all of these. Let's keep calm and do some quantum mechanics. how can we work with this? Let's try to understand the basics of the quantum mechanics. First thing we have to change. Probably you have seen this sitcom, and probably you recognize this logo in the Big Bang Theory name, that could be an atom with the electrons and so on. But this is the Rutherford models. That is not true. We don't have a very ball inside an atom that is a nucleus, and some small balls, probably blue balls, smaller than the nucleus, that are orbiting around this. This is some kind of planetary model of an atom. This is not true. This is not a quantum system. Through the years, we have understood more how is this working, and Schrödinger in 1926 they said that the atoms inside is something like a nucleus, and something that could be a place to find an electron. But there is not small balls that are the electrons. This is an atom. We have some kind of probability clouds in which we can find an electron. And this is one of the things that we can try to use in order to make some quantum algorithms. But we need to change our mind, because we are changing our view of a classical world with balls, with objects, and even with weights, to a quantum world in which we have no knowledge about it, and in which everything could be a particle and also a wave at the same time. And depending on the observer and depending on the system, it can manifest like a wave or like a particle. So this wave-particle duality is a problem for us. But we can try to understand this, or we can try to use it. But Heisenberg said that there is some kind of uncertainty principle. This is, we cannot see the position of a particle, of a quantum particle, and see how it is moving. So we don't know where this kind of quantum particles, electrons and so on are. But this is good for us, because this can help us in having real random systems. So this is an approach for quantum computing. Probably you have heard about the Schrödinger cat. The cat is inside a box. There is something like a vial of poison. Before opening the box, you don't know if the cat is alive or is dead. So he's dead and alive at the same time. This is what is called superposition. And the cat could be 50% of the times dead and 50% of the times alive. Is alive. But I think that it's easier to understand with this example. These are the Schrödinger plates, or dishes. The plates are broken and not broken at the same time until you open the door. Probably some of them will remain on the shelf and are not broken, and others will fall down and will be broken after the opening of the door. This is a superposition. And we are going to have some kind of computer variables in which we don't know in which state are but we can work with this kind of superposition. So this kind of variables would be true and false at the same time until we observe it, until we measure it. And also, we will have the entanglement. Entanglement is that we can have two particles, two qubits, two variables that can perform in the same way, that act in the same way. So we can have two variables, send one of them to the moon or to the space, open space, or to another continent, and when we observe the variable I have, the other will have the same value when it will be observed or measured. So this is another thing that we can use. And one of the things that can be used in this kind of characteristic is because we can have in our CPU processor several registers that can be entangled, and we can change or send information from one part of the processor to another one with this kind of characteristic. And also we will have the teleportation, but not in the Star Trek way of saying the teleportation. We are going to have some variables that can be sent to another place instantaneously. So we can teleport information even faster than the light, the speed of the light. But, and this is one of the things that we have to know about teleportation, there is the no cloning theorem. This means that you cannot clone a variable. So, no more variable A equals variable B. This is not allowed in quantum computing. And in order to teleport something, we need to kill the variable in its previous place in order to be sent to the other place. This is a handicap, but we can try to use the system with the quantum mechanics laws. So, how can we use this? First thing, what is a qubit? A qubit is something that is not true or false. It's something that is true and false at the same time. And we are going to work with it in this superposition state. And after that, we can see what is the results of our operations. So this could be a representation of a qubit, and you can see that if we measure this qubit and we have found our electron in the north hemisphere, it could be a 0, and if it's in the south, it's a 1. If it is in the western, it's a minus, and it's in the eastern, it's a plus. So we can try to work with this. But the good news about that is that we can also interfere, we can make some operation with this qubit in order to have more probability to have a 0 than a 1. So probably it's not 50-50%, probably it says 10 and 90% and something like that. All of this is represented by this kind of notation in a Hilbert space, but I think I'm getting out of time, so I'm not going to get into this kind of mathematical notation, and I'm going to go on with the computing part. So we can see that, let me go, these are classical logic gates. This is an OR and a NOT. This is an AND gate and an OR and a NOT gate. In quantum computing, we are going to have something similar to that, but are not intuitive gates. We are going to have the Pauli X gate, that is a NOT gate. This is the intuitive one. So we can negate a qubit. But we have a lot of more gates that we need to understand in order to work with this kind of quantum computing. So the set gate flip the phase of the electron, change its phase. The Hadamard gate put a qubit in superposition. The T gate rotates the qubit around some axis, and also we have some kind of control gates in which, for example, we have the control NOT that will negate the second qubit if the first is true when it will be measured. Not now, because now both of them are in superposition. But when we will measure the first one, if it's true, the second should be false. This changes the perception of computing, of quantum computing. There is more gates like this, that is a control NOT. And this, the Toffoli gate, is one of the universal operation, because in using this kind of gate, we can create a NOT and an AND gate. How? Here, using this is a quantum circuit, and we can create some kind of circuit in which we can use two X gates and one Toffoli gate in order to get a NOT gate. And we can create an AND gate using this Toffoli gate. We need to understand it in order to create the basic blocks in which we are going to work for creating better quantum algorithms. There is a lot of examples, and now there is a lot of quantum platforms. The more known and more useful platforms are these. This is one of the best quantum simulators that you can use in order to make prototypes. This is, if you go to that address that is at the bottom of the slide, you can start working with quantum circuits, and you can use up to 16 qubits, and it's working on your browser, on your web browser. But it's not a quantum computer. It's a simulation of a quantum computer. But you can use the quantum computing of the IBM. You can register at that address, and you can use the smaller quantum computer by IBM. You can use up to 16 qubits. And as you can see here, it's very similar to the quantum circuit that we have seen. And also, there is another kind of systems that there's another kind of quantum computing based on Hamiltonian paths and also on the quantum annealing systems. So we can try to find a solution of a optimization problem using finding the lowest energy of the system. You can register also on this address, and you can have 1 minute per month of quantum computing time. let's see some kind of quantum circuits. We have seen that before, but the best thing is that we can make some kind of entanglement between two qubits with this easy and simple quantum circuit. And these green bars means that you can only get 0, 0 or 1, 1. So this is a quantum equivalent to a conditional if in another language. And you can see that you can put it in the IBM computer, and in the bottom of the slide you can see that we can have the 0, 0, 0, 1, 1, 0, and 1, 1. And you can see that we have about 20% of the times a bad solution. This is due to the quantum noise. Well, this picture is about 1 year old. Now it's about 5% of errors in the quantum computer. But the best thing about this is that this is very, very fast. So you can run your algorithm about 1,000 times and get the most repeated solution, and that will be one of the solutions without noise. And in base of that, we can, for example, make one full adder. This only add 2 bits and a carry bit and get the solution of adding 2 bits, but in a quantum way. So we get all the sums in only one computer cycle. So we get all the solutions in only one cycle. But there is a lot more. For example, the search algorithm. This algorithm is simple. This is a schema of this, but we can, you can see the H, the blue H. This gate is for putting all the qubits in superposition. We don't know the value of these qubits. And after that, we use that gate U sub F, that is something like an oracle. In this gate, we are going to put the constraint of our problem. And after that, we are going to rotate our qubit around some axis in order to have more probabilities, a lot of probability of getting one of the solutions that fulfill the constraints in the oracle gate. And you can see that how is this working. At the beginning, all the qubits are with the same probability of being true or false. But after some stages, you can see that this green bar at the bottom of the system is growing until in the end is about 99% of probability of having the good solution. The oracle was saying that we want to find the 11011, and you can see at in the right part that we have found this solution. It's a very simple example, but if we make this oracle complex enough to describe our problem, we can use this kind of algorithm for solving, for finding solution to our problems, even complex optimization problems. And it's very simple. You can see here the same algorithm in a real quantum computer. This is the IBM quantum computer, and I have run, I only use 3 qubits, And I was looking for 1, 1. That was these two kind of bars. And it's working, and this is almost instantaneous. You get in no time this solution. And this is the most dangerous algorithm, because, as I have said, this is the one that will change the cryptography. But it's easy. It's a very easy algorithm. It's not easy to understand, but it's easy to implement, because it's based on the quantum, on the Fourier transform, on the quantum Fourier transform. And using that, we get the factor, the integer factor of very large prime integers in almost no time, in about 2 minutes. So we need to do something in order to circumvent, to solve this kind of problem. Here is the Shor algorithm in a real computer, in the IBM real computer. Only 4 qubits, but it's working now. If you have 50, 60 qubits, you can decode all the current cryptography systems. This is a problem. And this is the new approach to quantum algorithm. I have not enough time in order to explain a lot of things, but I want to introduce all of the things that are working here. The quantum annealing is based on trying to have some kind of system that is with the same probability of have one state or another. But working with the energy, we can try to get the solution of our problem by reaching the lowest energy of our system. And this is working. You can see here. This is similar to the optimization problems in which we try to find an optimal place, and we have the local optimum problems and something like that. With quantum computer, we can reach this solution in almost no time, but trying to get to a system that has lower energy than at the beginning. We need to specify our problem. How? Using a Hamiltonian system, but this is working now. And I know that there is a lot of systems that that is working on this kind of solutions and are getting very promising solutions. For example, for traffic commuting or for GPS systems and something like that. And I want to tell you that I think that quantum computer computing should not be only quantum gates or only mathematical descriptions. So I think, and we think, that there is a need for quantum software engineering. So I invite you to get to that address, to read the Quantum Software Engineering Manifesto, and if you like it, sign it. Because we think that there is a need for more research in quantum software engineering. And I have finished. I think that I have been about 5 minutes later for what I need, but I'm open for your questions, for your suggestions. If you have more questions after this, you can write me an email, and I'll try to do my best to answer your questions. I'm going to stop sharing my screen and we can try to discuss this kind of system of things.
Thank you very much, Dr. Manuel Serrano. There was a couple of questions coming in the chat. So please, I encourage all of you to write in the chat any questions. One of the questions is, can you show us a basic example of a practical application?
Oh, well, I think that I can. For example, let me. I cannot show you because I cannot connect to these quantum computers just right now in this computer, but I'm going to show you some real problems that you can see. For example, let me share this. Here, you can see the NASA problem, the n-queens optimization problem, maximum cut, antenna selection. These are classical optimization problems. And for example, we can see here that that we are going to specify our problem with a Hamiltonian. This means that we want to have to maximize the number of the value of the minimize the value of the object that are in the back, and we want to minimize, in this case maximize, the weight of the objects. So specifying by this, we can here's the Python algorithm. We can, here we are working this is the mathematical representation of the Hamiltonian, and after that, if you want, you can try to run it and you get the best solution for the knapsack problem. This is, for example, one of the classical applications. There's
a question related to that, actually, quite interesting. Is there a higher level programming interface that can be used? So the example, it seems like we can use Python,
yes.
And that means there are definitely, Python doesn't have the first class citizens of quantum programming. So do you think there is a higher level programming language or interface that could be used?
Yes.
The question actually says, do we have to use Hamiltonian annotation for quantum computing?
Well, these are two different questions. The first question, is there a higher level programming interface for Pauli gates? Yes, there are two principal languages. One is Python, that is used in the IBM systems, and there is another language that is promising. This is Q# from Microsoft. Microsoft doesn't have a quantum computer now, but is working to implement the quantum language into the .NET core, so you can connect in the future with all the systems that can be with libraries or so on. So Python and Q# are the two languages, higher level languages that can be used. The other question is, do we have to use Hamiltonian annotation for quantum computers? It depends. There are two approach for quantum programming. First one is quantum gates approach. In this case, you don't need to use Hamiltonian notation. The other approach that is in that moment is more promising is the D-wave systems that are based on Hamiltonian notation. So it depends on your needs, and it depends on the quantum platform you are using.
Thank you. I hope that answered the question. There's another question. What are concrete problems quantum software engineering has to solve?
Wow. I don't understand the question. I think that the question is about how is going how can we use software engineering in quantum computing, I guess.
Just 1 second. By the way, I have unmuted you all, or you now have the capability of unmuting yourself. So if you would like just to clarify your questions, etc. Please
yes,
do so.
Here is Michael, exactly. This is the question. I mean, how can software engineering knowledge that we have help to solve problems for quantum programming, computing, whatever?
So your question is about how quantum computers will solve problems.
Yeah, which problem needs software engineering knowledge? So, or what problem should we address in quantum computing based on our software engineering background? Should it be some modeling language? Should it be some testing approaches? Whatever.
Well, at the moment, there is not quantum software engineering. So, people, programmers, coders are working with quantum gates and with Hamiltonians. This is not software engineering. So, no everyone need to be a software engineer in order to code a program in C, Java, JavaScript, or Python. But we think that this will be grow, and probably we need some kind of software engineering approach in order to get more complex programs that will come in the future years. And there is another approach for the software engineering approach, is that probably in the future we are going to have hybrid systems with some classical computing and quantum computing. At that moment, probably you need to use software engineering for mixing those systems. But at these times, we only have quantum gates and quantum annealing. I have answered your question or not?
Yes, thank you.
Okay, thanks.
Professor Manuel, my question is, you have answered my question before. You said that there is a Python interface for those Pauli gates. So basically, this Python framework just provide a Python API for Pauli gates to manipulate those Pauli gates, right?
Can you write your question, because I don't hear you. I heard you with low volume, so I couldn't understand you.
Just to while the question is coming or being written, there's a question that is quantum computing and quantum computers two different concepts or the same?
Yes, two different concepts, but they are related. Quantum computers are the hardware. Quantum computing is the software. Is that? So quantum computing is making some programs, saying quantum algorithms for quantum computers.
Okay, maybe we thank you for the answer. I think it's clear. So maybe we can have again the question.
Okay, so Jorge Eduardo says, the last algorithm optimization that you show us is much better using quantum computing in comparison with conventional optimization. What is the difference in performance? Okay, so for a small set of objects, it's better to use a classical approach. And this kind of problem, the knapsack problem, is there is a very direct solution with a heuristic approach. And for about 10-20 objects, it's better to use a classical algorithm. But when the number of objects is growing to a very big number, for I don't know, about hundreds of thousands of objects or something like that, probably a classical computer cannot solve this problem in time. So at that time, the quantum computer is solving with very good times. So there is difference, but with when you are approaching a very big number of objects. The next question is, the Python interface nowadays only provides a way to manipulate Pauli gates. It depends on the platform. If you are working with, if you are working with the IBM quantum computers, you are manipulating Pauli gates. No, however, IBM is working on implementing some higher level algorithms. So you specify your system in like a matrix, and you are calling some methods that solve the problem without implementing the quantum gates. On the other hand, when you are working with the D-Wave systems, you are not going to use Pauli gates. So with Python, if you are connected to the D-Wave quantum computers, you are only specifying a matrix of constraints, a matrix of benefits, and you are asking the computer to solve this. And the D-Wave system transform this matrix to the qubits and gates without your knowledge. You don't need. You can see it. If you want, you can connect to the web, and you can see how your problem is solving. But you are not manipulating Pauli gates in that kind of platform. The next question is Balaji Anka asked me, do you think quantum computing can alter the outcomes more efficiently or only produce speed up in their computations? I think that both of them, because they produce speed ups in the computation. This is true, but also quantum computers are very efficient when we are talking about energy. A quantum computer is about 25 kilowatts by hour, and the algorithms usually are solved in about milliseconds, so they are more efficient than the classical computers. And this this energy that is wasted, the 25 kilowatts per hour, is including the refrigeration. of the computer. So they are more efficient than classical computer. I don't know if, what Spanos Lover is saying with polynomial time.
Hannes, do you want to clarify your? Are you asking a question or is it a comment? Maybe he meant the efficiency, maybe, or the speed ups. Is it in polynomial
Yes.
time?
Well, in fact, yes, quantum algorithms usually are in polynomial time.
Okay.
Usually, there are algorithms that are less than that, with so are very efficient. Yuan Kunxi asks, what about the detection of qubit? Is it still a problem for quantum computing? Have to repeat many times to get the accurate answer? Yes, there is a problem with the quantum noise, because this is there are a lot of ambient environment noise that can change the results. So usually you are going to repeat your algorithm usually about 1,000 times, and you get the more repeated solutions, because there is a lot of problem with noise. They are working on that, and they are improving the computers and also improving the error detections. But now you had to repeat many times your algorithm in order to get accurate answers. Okay, so Jorge Eduardo asked me, what are the basic steps to learn quantum computing in daily problems or crucial ones? What is the most promising field to use quantum computing? Okay, what are the basic steps? Probably try to understand what are the quantum gates, in order to understand how useful are these quantum gates for our for quantum algorithms. After that, probably you have to work on quantum Fourier transform, quantum phase amplification, and oracle building. This needs you to understand how to use complex numbers, eigenvalue, eigenvectors, eigenstates, and also you have to learn about Hilbert space. After that, you can start by learning the basics algorithms, and these are the two that I have talked about, that the Grover and the Shor algorithm. And after that, probably you can start trying to understand the Hamiltonians and the other approach, the adiabatic and quantum analytic programming. This is the way I did about 2 years ago. But if you are more interested in quantum optimization, probably you can start by understanding quantum annealing. What is the most promising field to use quantum computing? The most promising field, I guess, is the optimization problem. In fact, Volkswagen is working on traffic optimization, and there is a lot of optimization problems that are now being solved with quantum computing. So probably this is the most promising field.
So we have a last question.
The last question.
Yeah.
Okay.
What's the difference between IBM quantum computing and D-Wave?
Okay.
So that's one part of the question.
Okay, this is the first one. Okay, what's the difference? The difference is the approach. The IBM approach is quantum gate based, and the weight systems is based on quantum annealing. This is the main difference. Why quantum computer from the weight consists of more qubits? Because all of the qubits are not correlated with each other, only correlated with the same. No, this is not the things. This is because the weight is cheating, probably, because they use hybrid systems in which they have some real qubits, some real quantum qubits, and another logical qubits that are not quantum, that are simulated, and they combine both of those worlds, of this world, in order to get more qubits. But it's not a real quantum computer.
Okay, thank you very much. I think we've already overpassed our time, and thanks everybody for attending actually and asking all the questions. So let me as well thank on behalf of everybody attending today, Dr. Manuel Serrano for this exciting talk, and actually you've opened, I think, us many questions and many more horizons in this talk. So thank you a lot for this talk and for your time.